So we're going to go a little deeper with projectiles at an angle. First thing we're going to do, we're going to come back to the same problem, and we're going to draw a graph for it. Okay, so we're going to graph this. We're going to do graphs for position and velocity. And so we're going to start with velocity. And so we have Vx versus t, and then we'll split it, and we have over here Vy versus t. Okay, so if you remember, I believe the horizontal component for x, let me find that. Okay, so I went back and found these. So remember, to find our components, we multiply the magnitude of the velocity times the cosine of the angle for x, and then for the sine of the angle for y. So we have our horizontal velocity, we have our initial velocity for y, and then we know the acceleration is downward at 9.8. I'm also going to say for this one that positive is up. And these are things that we know from the beginning, and then situationally we can determine the final velocity or the vertical displacement depending what we're looking at. Okay, so we know that if we draw a velocity graph, we're going to sketch it something like this. Okay, this point right here represents when it gets to the highest point. And so the area right here is going to be the displacement at highest point. Okay? And so I believe we found it was something like 8 meters in the last video. So the area there would be equal to 8 meters. And then if we were to add to it the combined area, so this is going to be, the area here represents how far it falls. And this would be like after the highest point. Okay, so if we went 8 meters here, and then we fell all the way down to here, well, if we're going to end up 40 meters below where it started, then the number we would add to 8 to bring us down to 40 meters below would be negative 48 meters. So the area of this part right here would be negative 48, and so 8 minus 48 gives us a vertical displacement of negative 40 meters. Okay, so from the start to the finish, we ended up, when we hit the ground, we ended up 40 meters below where we started. Okay, that area here was how much we gained going up, and the area right here is how much we fell after that highest point, and we can combine those for our total displacement. Okay, I believe that our final velocity here was something like negative 30 meters per second. Okay, this was like 12.5. Okay, some other things, if we were to graph the position, we'll do position as opposed to displacement. So we start up here at 40, and it's going to look like this for y, highest point. Okay, and then for x, let's look at x now. Horizontal velocity going to look like this, constant velocity of 21.7 meters per second. Remember that the area here is that horizontal displacement. Okay, so if we, we'll come back to that. And then if we want to graph the horizontal displacement or the horizontal position, it's just going to look like this, always moving forward at a constant speed. Okay, so from here we're going to go ahead and develop functions for each of these graphs. Okay, so we'll write a function for Vx, a function for x, a function, we'll actually use delta x for this one. Then we're going to develop a function for Vy and a function for delta y. Okay, so to start with Vx, so for x we're going to use equals V naught plus AT, and delta x equals V naught t plus 1/2 AT squared. In both of these cases for x, a is equal to 0. And so Vx here, V initial for x is 21.7, so this is just equal to 21.7 meters per second. For this one right here, initial velocity, V naught, 21.7 times our time, And then this term goes away again because acceleration is 0. So these are functions for the horizontal position for x. For y, to find those functions, okay, go ahead and use this equation right here to find the function for the vertical velocity. You should get initial velocity of 12.5 meters per second plus negative 9.8 meters per second squared times t. Go ahead and do this again for the displacement. Write a function for displacement. You should get 12.5 meters per second t minus 4.9 t squared. Okay, so now we have functions for all of these. And when I showed the simulation I showed you in the last video, I actually used this function right here and this function right here to develop that simulation. Okay? Alright, and then the next thing I'm going to show you is just a couple different kinds of problems like this that you might come across, so you have some experience with them before you run into them. Okay, so here I have a scenario where I have a projectile launched from about ground level, and the question I want to answer is just well, two things. I want to find out how far away it's going to land, so like what the range of this projectile is, and I also want to know how high it's going to go. Okay, and then I also want to be able to kind of figure out its coordinates at any time as well. So we're going to go through all those three things, but before we can even start, what's the first thing we're going to have to do? Well, we need to find the components for the velocity. Okay, so go ahead and find for me Vx and Vy. Okay, so we have this horizontal velocity. We found it by multiplying the magnitude of this times the cosine of 40. So Vx is equal to 306 meters per second. For the purpose of this problem, we're going to say up is positive. And so Vy, our initial velocity for y, 400 times sine of 40, going to give us 257 meters per second. Okay? And so the first thing I want to find, if this is the path of the projectile, I want to find how far away it's going to land. Okay, and that's the value of delta x. Okay, a horizontal displacement. Okay? Now, the problem is, in order to find our delta x, we need to know how long it's going to be in the air for. Okay? And so in order to do that, we need to figure out, okay, well, how much time is it going to take to get to here? Okay? And for that we're going to use our y information. So we know that our initial velocity for y is 257 meters per second. And our acceleration is downward at 9.8 meters per second squared. And so we need to solve for the time, okay? Before we do, we actually need one more piece of information. So there's actually two things that we know about this position right here. Okay, we actually know the vertical displacement and we know the final velocity there. Okay, what would be the displacement at that position? It would be 0 meters. Okay, what would be the velocity of that position? Well, remember that whatever our initial velocity is upward, when it returns that starting height, it's got the same velocity but in the downward direction, so it's the opposite. So at that position, it's going to have a velocity of negative 257 meters per second in the y direction. Okay, so given that, we can actually use any of the three equations or any of the equations that have time in them to solve for time. Okay, so that's up to you. So go ahead and find for me how much time it's going to take to get from here to here. So we get a time of about 52.4 seconds. I used this equation right here. You could have also used the delta y equals v naught t plus 1/2 at squared and got the same thing. So we have a time of 52.4 seconds. Go ahead and use that now to figure out how far away it's going to land. Okay, so I went ahead and did this as well. We used our constant velocity equation here since it's moving at a constant speed horizontally. And so delta x is equal to v times t, 306 times 52.4 seconds, going to give us 16,000 meters, okay? And so it's going to land about 16,000 meters or 16 kilometers away from where it was launched. Okay, the next thing that I want to talk about is how high it's going to go. So what's going on at this point right here? Okay, so before we can do that, we need to kind of look over here and change some things. At this point, the vertical displacement is not 0, and the velocity is not 257. Also, the time, not 52.4 seconds. Okay, so what things do we know about this point right here? I can tell you that we know the time, and we know the velocity there. Okay, so what's going to be the time there, and what's going to be the velocity there? Well, the time would be actually half of this value, so half of 52.4 is going to be 26.2 seconds, and the velocity at that point vertically is 0 because it's at its highest point, so 0 meters per second. So now you can go ahead and solve for the height. Okay, you could use either of the two equations because you have 1, 2, 3, 4 values, so you could use any of the equations with displacement to solve. Okay, so go ahead and find that. Okay, so I use this equation right here, and we got a vertical displacement of about 4,190 meters, so over 4 kilometers into the air. Okay, and now just a note about using this physics to analyze this projectile. This projectile is going really, really fast, and I'm going to say that probably when it's going that fast, we're going to have a much greater effects from air resistance. And so while with a lot of stuff we're pretending there's no air resistance, if we were actually analyzing this particle or this projectile, we'd really have to take into account air resistance, which really would make this a much more complex problem. And we'll talk a little bit about that next semester, but things just start to get really, really tricky. Okay. The last thing I want to do is find functions for position for x and for y. Okay, I'll do the x one. So for x, it's going to be vx times t. Okay, so it's going to be 306 t. And then for y, I want you to go ahead and find that. Remember, we can use this delta y equals v naught t plus 1/2 at squared equation. Okay, so you should get something like 257 t minus 4.9 t squared as your function for y. Okay? And if you ever were asked, what are the coordinates at this time, then you could take the time and plug into those functions and get the coordinates. Okay? So the coordinates at time 0, we plug in 0, we get 0 for x. We plug in 0, we get 0 for y. Okay, and so here's another example that we've gone through with projectile at an angle. One other thing I want to mention is just the effect on the starting angle on the range of the projectile. Okay, the last thing I want to mention is just a quick thing about the range of a horizontal projectile launched at an angle, and the range of it when it's launched from ground level. So when it's landing at its starting height, I want to talk about maximizing the range. Okay, and what we're going to find, and so I'm going to cycle through a bunch of values for the angle, and I want you to try to figure out at what point the angle is, at what point the projectile is going to land furthest away. So if you look here as I kind of scan through this, it looks like the maximum landing spot happens kind of around here. Okay, and that looks like about like 63, 64. Okay, and so you're going to see that that is going to occur. So here's like 37 degrees, this is 39, 40, 42, 43, 44, there's 45, and then you're going to notice it'll start to come back. Okay, and what you'll find if you were to try this out with all the different angles you could is that the maximum range for a horizontal projectile is when the angle is 45 degrees.